We'll wait for a couple more minutes for people to join and then get started. Hope you can hear me and see my slides. If not, please leave a message on chat. Let's wait another minute and then start. Looks like people are still joining. Okay, let's get started. So, good evening. Welcome to the live session for week 6 of the CS100 Operating System Fundamentals course. I'm Prashanti. I'm a second year PhD student at IISc Bangalore, and I will be handling all 12 live sessions for this course at this time. So, moving on. I think I've shown this in every week slides, but in case there is someone who's joining this for the first time, here's an overview of what you can expect from these sessions. So you have 3 of these sessions every week by different team members. The timings and the meeting links are available on the course page. And the point of these sessions is to focus on problem solving and to help you understand the concepts covered in the course clearly. So we will be dealing with questions for the most part, and those questions or problems will be similar to your assignment problems so that you can solve your assignments more easily. But they will not be exactly the same questions as what is there in your assignments, because you're expected to solve that on your own. And in case you have any doubts or questions that need clarification from that week's course content, feel free to ask them in this session. I will pause 2 or 3 times through the 1 hour session so so that people who join at different points get a chance to ask their questions. But feel free to post those questions anytime, right? And we will be taking questions on chat because it gets difficult to handle audio when there are more than 10 people in a meeting. So yeah, please use the chat box for any questions, and post the session you will be getting access to the slides and the recording from the NPTEL course page under announcements. So hope this is clear. So if you have any questions on the logistics side, please post them on chat again. I'll wait for a few more seconds and then move to this week's content. And in general, I like to keep the sessions as interactive as possible because it helps me better understand what you're looking for from my explanations, and that way I can tailor those explanations to focus on things that need more explanation. For instance, if many people are confused by two options in a question, then I can spend more time addressing the doubt or the confusion with respect to those two options. So whenever I read out a question, I will pause for 30 seconds to see if anyone has an answer to that question, and post whatever you think is the answer in the chat box. It doesn't matter if it's right or wrong. This is not a test. You are not going to be judged based on what you post, right? And after I discuss the answer to the question, I'll again wait for 30 seconds to see if you have any doubts on my explanation, and again you can post a question on chat. I see that someone has a raised hand. Is there a question? If there is, please post it on chat again, because you can't unmute, so feel free to post a question on chat anytime. Okay, let's move on to the contents. So a quick recap of what was covered in week 6. So we mainly looked at scheduling algorithms, and we looked at a variety of scheduling algorithms starting from the shortest job first, and we spoke about how this is sort of an ideal algorithm and how do you actually go about predicting the CPU burst times. And then we looked at round robin, priority, multi-level queue, and SRTN, and multi-level feedback queue, and things like that. And after that, we took a brief look into synchronization. We looked at what are race conditions, what is a critical section, and we looked at concepts like mutual exclusion, progress, and bounded wait. So today's session and today's questions will be focusing on these topics. So let's start with the first question. This is a simple one. So let's start with this. Which scheduling algorithm is non-preemptive? Round robin scheduling, priority scheduling, shortest job first scheduling, first come first serve scheduling. Which do you think is non-preemptive? Any answers to this? D, first come first serve. Okay. Anyone else? Anyone who agrees with D? Anyone who thinks some other option is the answer? No other answers? Do people agree with D? Okay. So it looks like there is a consensus. Let's look at the answer. So it is D, first come first serve, or FCFS as it is called, right? And why is this the answer? FCFS schedules based on the arrival time, and if you remember the algorithm, it does not actually preempt workloads in between their CPU burst. Whereas if you think of round robin, there is a preemption after that time quantum elapses. And similarly, SJF and priority, while they do have a non-preemptive version, there are also preemptive versions of them, right? Like SJF had, I think, SRTN as its preemptive version. Priority also had a variant that was preemptive. So all of these are preemptive, and first come first serve is the only one that is non-preemptive. So is this clear, or does someone still have doubts with this? I'll wait a few seconds before moving on to the next question. If you have any doubts, please ask. Okay, if not, so let's do a quick scheduling recap, because many questions today are based on these scheduling algorithms. So in case you haven't looked through the week's lecture videos in detail, this few minutes of recap will be useful. So let's start with FCFS. So it stands for first come first serve scheduling. And here, so we look at a quick example. We won't dwell on these in detail because the lecture videos have already done that. I'll just spend a minute on each kind of algorithm so that it becomes helpful for you to answer these questions, right? So here you have P1, P2 and P3, and their burst times are 24, 3 and 3. And we assume the arrival order to be P1, P2, P3, meaning that P1 comes first, followed by P2, followed by P3. Now, if you have to draw out a schedule using the Gantt chart for FCFS, it looks like this. So P1 came first, so it executes for 24 seconds, P2 came next and it executes for 3 seconds, and P3 executes the last for another 3 seconds. In total, everything ends at 30. And just as a recap, so average waiting time is calculated by taking the waiting time of each process and then averaging it. So you divide it by the number of processes. So you sum it up and divide it by the number of processes. Here P1 does not wait at all. It is scheduled as soon as it arrives. P2 is scheduled after 24 seconds, so its wait time is 24. P3 is scheduled after 27 seconds. So you add up all three and the average waiting time is 17. So this is about FCFS. Let's move on to SJF. So here we schedule based on the length of the CPU bursts, right? So each process has a certain length of CPU burst time, and this is an assumption, right? We assume that we know this. And given this, if you schedule it using shortest job first, you get the minimal average waiting time, in the sense that SJF is optimal, right? So let's look at a quick example. So P1, P2, P3, P4 have burst times of 6, 8, 7 and 3, and their arrival times are 0, 2, 4 and 5, right? Now here at time instant 0, the shortest process that you have, P4, has a burst time of 3, which you schedule, followed by P1, which has a burst time of 6, followed by P3, which has a burst time of 7, followed by P2, which has a burst time of 8. And your average waiting time is therefore 3 plus 16 plus 9 plus 0 divided by 4, which comes out to be 7, right? So this is how SJF works, as in it takes the burst times and then schedules the shortest one first. It, in a way, it tries to minimize the waiting time across all processes. So let's move on. We have a preemptive version of SJF called shortest remaining time first, and here's an example for that, right? So in this case, P1 arrives at 0 and it has a burst time of 8. So we schedule this for 1 second, after which P2 arrives with a burst time of 4, right? So we schedule P2 because now at t equal to 1, P2 is the shortest, is the process with the shortest burst time. So we schedule P2 and it runs for t equal to 2, at t equal to 2 P3 arrives, but P2 is still the one with the shortest remaining time, right? So P2 continues running, and then at t equal to 3 P4 arrives, but again P4 has a burst time of 5 and P2's remaining time is less than that. So P2 continues running till it finishes. Then what is left now is P1, P3 and P4, and P4 has the shortest remaining time, which is 5. So P4 continues running, so it will consecutively have 5, 4, 3, 2 and 1, and at each point there is no other process which has a shorter remaining time. So P4 continues running till it finishes, followed by, now there's just P1 and P3 left. So P1 runs next for 8 seconds and then P3 for 9 seconds, and then you get the average waiting time by summing up all the waiting times and dividing by the number of processes. And the difference between SJF and this is that in SJF you didn't actually have this notion of preempting workloads and taking into account the shortest time at that particular instant, right? Here at every instant you're checking which is the shortest one next that's left now and then scheduling that. So we did not have that notion in SJF, and that was a non-preemptive variant, whereas this is the preemptive version of it. And let's do a quick recap of round robin as well. So in round robin, the idea is that each process gets a small unit of CPU time, which is referred to as a time quantum. After this has elapsed, it is preempted and added to the end of the ready queue. So if there are n processes in the ready queue, then each process gets 1 by n of the CPU time in chunks of at least queue time units. It cannot get more than queue time units at once, because that's how we define this time quantum. And what round robin tries to do by this notion of time quantum is that there is a bound on the waiting time. No process needs to wait more than this n minus 1 star queue. So this is in a way trying to address fairness, as in if you are a process who comes very early, you shouldn't have to wait more than this time, and this guarantee will be fulfilled by round robin, right? So let's look at a quick example. P1 takes 24 seconds, P2 3, P3 3, and the time quantum is 4 here. So P1 runs for 4 seconds followed by P2, but P2 only needs 3 seconds. So it relinquishes the CPU after 3 seconds because it has finished running. So at t equal to 7, P3 starts, and the same case, it also runs only for 3 seconds because it does not need any more, and gives back the control to P1. Now P1 runs for the full time quantum of 4, after which again there is a scheduling decision that happens, but since there is no other process that is eligible to run, P1 continues running, and this repeats at every multiple of 4 till P1 finishes execution. So ultimately the execution ends at 30 seconds. And I think the last recap that we have is the priority based scheduling. So here you have a way for some processes. So with all the previous scheduling algorithms, every process was considered equal, right? Like for instance, with round robin, you are basically saying that all processes are equal, and we'll just put them in a queue and each one will get to execute on the same quantum of time. And with first come first serve, we treated different processes differently based on when they arrived, right? So in each of these algorithms, there is some amount of differential treatment based on different aspects. So in one case, it was arrival time. In one case, it was just that every process is equal. In another process, in another algorithm like this one, the priority scheduling, it is based on priority, which is a number associated with each process. And you could have some convention like this where the smallest integer corresponds to the highest priority. And then again, you can have a preemptive and a non-preemptive version of this algorithm. So what you do here, let's take an example again. So you have 5 processes with different burst times and different priorities. Now what you do is the priority 1 is basically P2, which has a burst time of 1. So that runs first. Now you cannot look at these burst times, you just look at the priority because we schedule based on the priority. Then we have one process with priority 2, which takes 5 seconds, so we schedule that. Then we move on to priority 3, which takes 10 seconds, and we finish scheduling that. And then we look at priority 4, which has a burst time of 2, and then finally priority 5, which has a burst time of 1. And then we, as usual, calculate the average waiting time. So with this, I think our quick recap of scheduling algorithms is done. So this will help you answer these questions better, at least that's the hope. So let's move on to the question. So this one says, among all the CPU scheduling algorithms, which is the most simplest? And your options are FCFS, SJF, round robin, none of the above. So we looked at all 3 with an example now. So which do you think is the simplest, in the sense the simplest to implement, or which doesn't involve a lot of complexity, right? What do you think the answer is? Any guesses? Okay, I see someone saying A, FCFS, B, none of the above. Okay. A, FCFS. Okay. Anyone else? Okay, so it's mostly between A and D then. Let's look at the answer. The answer is FCFS. So let's talk about SJF for a minute. So with SJF, you need to know which is the one with the shortest burst time. That itself is not easy, right? How do you know about this? So we saw in the recap slide, I think there were a couple of points on that. So we could ask the user, for instance, but what if the user lies, right? So suppose the user doesn't know, then what then? How do you figure out what is the burst time? And then you would also need to maintain this data structure, which is sorted by their burst times, and every time a new job arrives, you would have to make sure the property of that data structure is maintained so that you can access the shortest burst time easily, right? This doesn't sound very simple. And in round robin, you have to maintain this sort of a structure where you insert at one end and then you remove at the other end, and you also have this notion of a time quantum, so you need something to interrupt execution once that time quantum has elapsed, right? Whereas think about FCFS, you just need a queue and you put processes in the order that they arrive and you just take them out and execute, right? So it is the simplest in terms of the infrastructure that is needed to support its execution. So that's why the answer to this is FCFS. Any doubts on this? I'll wait for a few seconds. If not, next question. The STF algorithm can be A. Preemptive, B. Non-preemptive only, C. Either preemptive or non-preemptive, none of the above. I think everyone knows the answer to this. What do you think? We went through this 5 minutes back, so I'm hoping you guys remember. A. Preemptive only. Okay. Anyone else? C. Either preemptive or non-preemptive. Again a C. Okay. The answer is C, because when we talk about STF, we also refer to its preemptive variant, which is SRTN, as we saw recently, SRTF, shortest remaining time first, and therefore there is a preemptive variant of STF. So you can have a non-preemptive variant, you can have a preemptive variant, or so the answer becomes C, which is either preemptive or non-preemptive. I think this is pretty straightforward, but if you do have questions, please ask. Moving on, if not, which is the most optimal but difficult to implement CPU scheduling algorithm? A. SJF, B. FCFS, C. RR, D. None of the above. What do you think sounds very difficult but is optimal? C. Round robin. Okay. B. FCFS. Okay. Does anyone think it's A? Okay, most people seem to think it's B or C. Okay, so let's look at the answer. The answer is actually A, SJF, and so let's talk about why this is the case, right? So how is SJF optimal? First of all, it's optimal in terms of the waiting time. So if you follow this shortest job first kind of scheduling, the average waiting time that you get is as low as possible. And why is this the case? It's sort of intuitive, right? You start off by scheduling the shortest one, followed by the next shortest, and so on. So at each point you're trying to minimize. So think of this. Let's see if I can get a pen sort of thing. Yeah. So if you look at the waiting time for this process, which is P2, right, it has to wait for all the things before it. So all of this contributes to the waiting time of this, and the waiting time of this plays a part in the average time. So if you wanted to minimize the waiting time of this, what would you do? You would make sure that these things ahead of it are as short as possible. How do you do that? By consecutively picking shorter things at the beginning, right? So it would look something like this, shorter, and then this much, and then this much. Whereas if you picked the first thing to be your longest CPU burst, then everything that comes after it will have a very long wait time, and therefore your average wait time will go up. So if you wanted to minimize average waiting time, the ideal thing for you to do is to start by scheduling the shortest ones first. right? And in that sense, you cannot do better than SJF. This is the best possible average waiting time you can get, and the intuition is pretty clear why you get that minimum average waiting time. So if your metric that you're gauging these scheduling algorithms on is waiting time, SJF is optimal. So it becomes like a standard that you compare other algorithms to in terms of waiting time. So for instance, let's say you implemented your own scheduling algorithm, right? Let's say it's something completely different from all of these, and now you want to compare that against the best, which if you go by waiting time is SJF. So you would compute average waiting time for your scheduling algorithm, and then you would compare that against the average waiting time that SJF gives you. So SJF's waiting time becomes kind of a benchmark, right? So SJF is the most optimal one, but it comes with that caveat that you should know how long each process is going to run. So if you did not know this, there is no way for you to do such a scheduling. Whereas in case of things like this, FCFS, right, there is no a priori knowledge that is needed to do the scheduling. So processes came in a particular order and you schedule them in the same order. So you don't need to know anything about the processes. Similarly, in round robin, processes come in a certain order, and all you need to do is schedule each of them for a given time quantum. So it goes around in this ring. So if you have processes like this, you schedule each one for the same amount of time. You don't need to know how long a process is going to run or anything of that sort. But SJF is an exception. It expects you to know this, and because of that it becomes very complicated to implement it. So in your lecture videos, I don't know if you remember, but there was a whole lot of material on predicting the length of the next CPU burst. So we took into account things like the history of CPU bursts for that process, and then we tried to predict the length of the next CPU burst. And we saw that it is not so easy to do, and you have factors like how much does the very immediate previous sample play a role versus all the other samples that came much before, right? So predicting the next CPU burst of a process is not very easy, it's complicated, and therefore your algorithm implementation for SJF becomes that much more complicated. But in case you're able to do that, then of course it gives you that optimality, right? So by that logic, the answer to this question, which is the most difficult, most optimal but difficult to implement, the answer becomes SJF, because FCFS is very simple to implement and there is no notion of optimality that you get here, right? You're just executing processes in the order that they arrive. You don't get much out of that. And with round robin, the good thing that you get is that the waiting time is bounded, but it does not give you, it does not try to minimize the average waiting time, right? So in that sense, SJF is the most optimal. So was that clear? Are there doubts? I'll wait for 30 seconds to see if there are any doubts on this. No doubts. Great. Let's move on then. So I hope you didn't see that, but yeah, okay, this will require a little bit of computation, so feel free to grab a pen and a piece of paper because you'll actually need to work this out, and I will give enough time for that. So there are 6. So since we are at the midway mark of the session, I will pause here to see if there are any general questions on any content from this week 6 lectures. If you do, please post that on the chat, and I will take those questions up at the end of the session. Okay, if not, we'll continue. So there are 6 processes and the arrival order of them is like this: P1 followed by P2 followed by P3 and so on. And the CPU burst times are given here, right? 9, 1, 14, 2, 6 and 20. So assuming that we schedule these based on the FCFS policy, what is the average waiting time? Since this is a numerical, I'll give you 2 whole minutes to solve it. Take your time, solve it and then tell me the answer. Okay, D 16.83. Anyone else? I'll wait a little longer in case people are still solving it. Any other answers? Did anyone else get D or do you have different answers? Okay, I see another D. Let's look at the answer then. So it is D 16.83. So great, good that you got it right. Let's look at the Gantt chart for this, right? So FCFS is pretty simple. You schedule them in the order they came and you know that the order they came is P1, P2, P3, P4, P5, P6. So the schedule will be exactly the same. Now coming to how long it takes. The first one takes 9 seconds or milliseconds in this case since it's specified. Great. So that's 9 and then the next one takes 1 which makes it 10 followed by 14 milliseconds. So this becomes 24 and then 2 milliseconds. So this is 26 and another 6 milliseconds which makes it 32 and then 20 more milliseconds which makes it 52. Again, the assumption in all of these is, like I said in the last week's session, that the context switch overhead and the scheduling decision overhead itself is 0. Like we're assuming that P1 gets switched out at P1 finishes at 9 and P2 starts executing at 9. In a real world scenario, there would be some limited overhead while the scheduler figures out which is the next one to execute and then sets up that process for execution, right? But it's a fair enough assumption to make. So yeah, that's just something for you to keep in mind. So now coming to the average waiting time, we take the waiting time for all the processes and divide them by 6. So for P2 it had to wait 9 seconds and for P3 it had to wait this plus this, and so on. I am not sure if the math here is correct. I will check that. But it comes out to 101, and then divide that by 6 and you get 16.83, which is option D, right? So that's how you get this average waiting time. So any doubts on this? Yeah, this addition is actually wrong. This so for instance P3, right? P3 will have to wait for this 9 plus 10. So I will correct this before I upload the slides. Sorry about that. But this is how you get the answer. I hope the idea is clear. Oh no, actually the math is right? So P3 waits just for this time, which is 10, right? 9 plus 1, so this already takes into account that. I assume this 10 was the burst time. The burst time was actually 9, so this math works out. So it is 101 by 6, and that makes it 16.83. Sorry about that. Anyway, are there any doubts on this? Okay, I'm assuming that's no doubts. So let's move to the next one. So we have three processes here, A1, A2, A3, and they have arrival times of 0, 2 and 3, and CPU bursts of 5, 7 and 3 milliseconds. Which is the correct completion order of the above three under FCFS and round robin with a quantum of 2? So you have 4 different options. So think about this and post your answer on chat. I'll wait a minute since this involves a little bit of computation too. Okay, we have an answer A. Okay, anyone else? I'll wait a little longer in case someone is working this out. Anyone who agrees with A? No other answers? Okay, in that case, let's look at the answer. So the answer was B. FCFS is A1, A2, A3, and then round robin is A1, A3, and A2. Okay, let's see how that is. So FCFS is sort of a very simple thing to do, right? You take the order in which the processes arrived in and you execute them in that order. So A1 came first and that executes for 5 milliseconds. A2 came next, that executes for 7 milliseconds, making wall clock time 12. And then A3 executes for 3 milliseconds, making the total time 15. And they finished in the order A1, A2, A3. So that eliminates option A, which says it's A1, A3, A2. So out of B, C and D, we need to figure out the round robin order. So let's start with that. So initially there is just one process in the queue, which is A1, right? And the time quantum is 2. So from 0 to 2, A1 executes. And then you have A2, which is added to the queue at 2 seconds, at t equal to 2. So now at t equal to 2, A2 is at the front of the queue. So A2 is picked up and executed for 2 seconds again, because the quantum is 2. And then A1 is picked up and executed. And by the time A3 has arrived, because A3 comes at time equal to 3, right? So now A3 is in this queue and A3 gets a chance to execute for 2 milliseconds. At this point there are no other new processes running, so it's a simple queue where, let's say, A3 was picked out, right? So now you have A2 and A1, and A3 finished, and then you pick A2, you execute A2 for 2 seconds, then you pick out A1, execute it for 2 seconds. So each time you add it back, right? So you keep doing this, and so one cycle of A3 executes, followed by A2, followed by A1. At this point A1 is over, because A1 has executed for 2 here, 2 here, and A1's burst was 5, right? So 2 plus 2 is 4. So here it only executes for 1 and it is done. And the next thing in the queue is A3, and A3 has already executed for 2 milliseconds here, and its burst is 3. So it executes for 1 more millisecond and A3 is also done. And then there is just A2 left. So A2 executes for 2 and then the remaining 1, because it has executed once here, once here, once here, making it 6, and then the last one that is left of the 7, and it finishes last. So the order of completion, which is what is asked in the question, is A3, A1 and A2. And the tricky part here is the round robin part, right? Because FCFS is very simple. It's the order of arrival, whatever order of they came in, that is the order they will get completed. But with round robin, you have to remember that there is this queue and you keep moving around in the queue and picking different things to run. Once it finishes running, you will put it back into the queue. Why did we not consider A3 after 4 milliseconds? Okay, let me try and figure that out. Okay, we are at 0 and we start with A1, that makes sense. And at time quantum 2, we pick out. So let's draw out this queue, right? Maybe that will help. So we first have A1 and we pick out A1 for execution, and by the time A2 has arrived, so the queue looks like this. So there is just A2, right? So we pick out A2 for execution, but A1, which just finished executing, gets added to the bottom of the queue, and this happens at t equal to 2. Now we pick out whatever is at the front of the queue, which is A2, and we start executing that. That executes up to t equal to 4. In the meantime, A3 arrives and we add A3 to the back of the queue. But at t equal to 4, when we have to make this scheduling decision, we pick out whatever is at the front of the queue. So we pick out A1, and that's why A3 is not picked out at 4, even though it arrived before 4. So here what matters is what is at the front of the queue, right? And that depends both on the arrival time and whatever finished executing previously. So to the person who asked the question, is it clear now why A3 was not picked at t equal to 4 even though it had arrived? Great. So yeah, this is something that you have to keep in mind when you work out these scheduling problems, right? The arrival time, the burst time, what kind of data structure you are keeping in mind. Anyway, so here's another question. So consider P1, P2, P3, P4, P5, P6 with different priorities and with burst times like this. What will the average waiting time be? And you have 4 options here. Again, I'll give you 2 minutes because it takes a little time to work this out. Let me know when you have the answer. So we use priority based scheduling here. Any answers? A 25 milliseconds. Okay. Anyone else? Okay, A 25 milliseconds. Okay, in the interest of time, let's move ahead and look at the answer. So the answer was actually 18.5 seconds, B. Let's look at how that is. So we pick, and remember here the key is to pick the lowest integer value of priority first, because the convention was that the lower the value, the higher the priority. So P6 has the highest priority. It executes for 6 milliseconds, followed by P5, which just takes 1 millisecond, followed by P1, which is at 3, which takes 20. So that makes it 27, and followed by P3, which has a priority of 4, which takes 7. So 27 plus 7 is 34. And then we have P2 at 5, which just takes 3 seconds, and then we have P4, which takes 8, which makes it 45. And the waiting time from here is pretty straightforward. So P5 waits 6 milliseconds, P1 waits 7, P3 waits 27, P2 waits 34, P4 waits 37. Add all of these, sum them up, divide them by 6, and you get 18.5 milliseconds. I see a raised hand. In case there are questions, please post it on chat, because you won't be able to unmute because of the meeting settings. Is this clear, or does anyone have a doubt here? Okay, if there are no doubts. Moving forward, in which of the following options below only one process at a time is allowed into its critical section among all processes that have critical sections for the same resource? And your options are synchronization, mutual exclusion, deadlock, none of the above. So we move from the scheduling set of questions to the synchronization content. Any answers to this? So, what is it that where you have multiple processes trying to access the same resource and only one is allowed at a time? So, I see one answer saying synchronization. Okay. B, mutual exclusion. Any takers for C or D? Let's take a look at the answer. So the answer was B, mutual exclusion. And let's look at a quick recap as to what synchronization was and a little bit about this so that you remember this. So why do you need synchronization? When you have shared data and multiple processes trying to access that shared data concurrently, due to some race conditions, meaning non-deterministic execution, you might end up having an inconsistent state for the data. So maintaining this consistency requires some sort of mechanism to ensure that these processes cooperate, and this is provided both by the hardware and the operating system. So this is broadly referred to as synchronization, right? But this particular question asks about having a critical section and which only one process being allowed at a time into that critical section, and that is mutual exclusion, because as the name says, mutual exclusion means that if one process is in the critical section, no other process would be allowed to enter that critical section at the same time, as in it would be excluded. Deadlock is not something we have seen yet, we will see it a little later, so I won't get into that. But the answer to this is mutual exclusion and not synchronization, because synchronization is a general idea that you need some kind of mechanism to ensure that processes cooperate among themselves and access shared data, whereas this is a specific means of implementing synchronization, which is mutual exclusion. Hope that is clear. Okay, let's move on. Which of the following is the solution for critical section problem? Mutual exclusion, progress, bounded weight, all of the above. It's a very similar question. So what do you think is the answer? D, all of the above. Okay. Anyone else? Let's quickly look at the answer because we are nearing time, and it is all of the above. And let's look at this sort of this explanation, which is a recap from your week 6 course contents. So mutual exclusion, as we saw in the previous question, was that if one process is executing in its critical section, then no other process can be executing in that same critical section. Progress refers to this notion that there is some process that wishes to enter its critical section when no other process is executing in its critical section. Then you cannot postpone this decision of the selection indefinitely. So it essentially says that there must be some progress in entering this critical section. Bounded wait again says that there must be a bound or a limit on the number of times that other processes are allowed to enter their critical sections after a particular process has made a request to enter its critical section and before that request is granted. So you can't have indefinite number of times that a process is kept on waiting after it has made this request to enter the critical section. So these are kind of abstract ideas, right? And there are particular ways of implementing these things, but in general they are intended to solve the access to the critical section problem. And I have one last question, so I will spend 2-3 minutes over time for that and then wind up. Which of the following is incorrect about the time quantum Q in round robin scheduling? If Q is too large, it is equivalent to FIFO, first in first out. If Q is too small, context switch overheads are very high. If Q is too small, context switch overheads are very low. None of the above. What do you guys think? A, Q is too large, it is equivalent to FIFO. Okay. Anyone else? Also, we are almost at the end of the session, so if you have any general doubts on the course content, here's your last chance to ask. Okay, this actually, I would say that both A and B are true. So D should have been A and B, right? So never mind, these options are not great. But let's look at a recap of why this is true, right? So what happens if Q is too large? Let's go back to the recap. And yeah, so here you have round robin. So this is what here it says, if Q is large, it becomes equivalent to FIFO. So let's say in this example, my Q was 30, right? So what would happen? P1 would execute, it would finish at 24, and then P2 would execute, it would finish, and then P3 would execute and it would finish. So it's essentially equivalent to first in first out, right? Whatever comes first executes and finishes, because it is never preempted throughout its run because the quantum is larger than that. So that's what happens if Q is large. Whereas if Q is really small, let's say I have Q equal to 1, right? So I will switch out at least 24 times for this process, maybe a little lesser since the others end quite early. But I think there was a slide on context switches, yes, here. So we looked at varying the quantum. So here you have quantum size equal to 12, context switch equal to 0. and quantum size equal to 6, context switch is 1, and if the quantum is actually made 1, the context switches are 9. So this was an example. So if the quantum size is too small, we risk having a high context switch overhead. So that's something to keep in mind while thinking about the round robin algorithm and choosing the quantum. So I hope that's clear on the last question. So if it's large, it becomes equivalent to FIFO, and if it's too small, the context switches are too many and the context switch overheads are high. So option D ideally should have been both of those. So I will correct that and put up the slides. And do you have any questions on today's content? I think I had one other concept which I will include in next week's content, since we are already running past time. Any questions, any doubts, feel free to ask. I'll stay on the call a minute more to see if anyone has questions. But for people who don't have questions, thank you so much for joining in. See you next week. Thank you so much for keeping the session interactive and answering all the questions. Hope you learned something useful from today's session. Thank you. I see a raised hand. Again, if you have a question, please type it on chat. The meeting settings disable unmuting people, so please type on chat if you have a question. I'll wait for 30 more seconds and end the call.